So, my name is Benjamin Eltzner. I speak about dimension reduction on polyspheres with applications to skeletal representations, and I will define the possibly unclear terms. So the talk is structured as usual. We give a short introduction. We explain our method, and then we come to an application. So I will not give an outline. The principal problem we deal with for dimension reduction on manifolds is that we cannot simply generalize a very well-working concept from linear spaces, namely PCA, which relies crucially on linearity. And so there are essentially two classes of approaches, namely first tangent space approaches, which mostly ignore geometry and especially, also periodic topologies, for example, for spheres or tori or spaces like that. And on the other hand, intrinsic approaches which rely on the manifold geometry. And then we further split up these intrinsic approaches into forward methods and backwards methods, where forward methods build up submanifolds from low dimension, so start with dimension 1, 2, 3. So these usually rely on geodesics or structures like this, so we need good geodesics of some type and a construction scheme. And the other type of method is backwards methods, where we increase codimensions, so we reduce the dimensions step by step. And this means we really find submanifolds, and we need a good parametric set, of submanifolds. And so in this talk, I will really lean towards the backwards methods, because they seem to fit the application we have in mind. Now, what's a polysphere? A polysphere is just product of spheres of arbitrary dimension. Some people call this a torus, but some people strongly dislike calling this a torus, and so polysphere is also a term that's been used for sphere made of polygons by 3D graphics animators. But I think there's no possible collision here, so let me just call this a polysphere. And so almost all of the geodesics, as in the usual torus, are dense in a certain toric subset. And that's a bad thing, of course. And here's an illustration of geodesics that aren't dense, like these blue ones, and the red geodesic, which is dense. And only for a two-dimensional torus here. And also the symmetry group is not very high-dimensional. It's just the product of the spherical symmetry groups. And so the set of submanifolds is not very rich. So we have troubles for the forward approaches as well as for the backwards approaches. And the idea here is, that we have a space which is not so different from the polyspheres, namely spheres, where everything is nice. And we can do geodesic approaches like geodesic PCA or horizontal PCA, or we can do the principal nested spheres backwards approach. So our idea is to just do a deformation and this is similar in some sense to a tangent space picture, only that we take a sphere as a model space and not a linear space. And we do this because we think that actually for dimension reduction, a sphere has in some sense, nicer properties than linear spaces. Okay, so we have squared line elements for 2 unit spheres, so we do this recursively. So I just explained the atomic deformation for 2 spheres, and then it can be iterated. What we do is we just multiply with a volume factor that turns the sum of these these line elements into the line element of a high-dimensional sphere. And so in this sense, the sphere S1 is called the inner sphere because it's deformed, and the sphere S2 is called the outer sphere, which is not deformed. And now we have degrees of freedom, namely rotation and ordering of spheres, so choice of coordinates, and also which spheres are taken as inner and which are taken as outer spheres. And to fix these degrees of freedom, well, the rotation, we use the standard embedding into real vector space. We determine the Frechet mean and use a rotation along a geodesic to move it to the North Pole. And for the ordering, on each sphere similarly, individually. And for the ordering, we use the data spread, which is a variance-like quantity. We choose a permutation such that the spread is maximal in the innermost sphere and minimal for the outermost for the outermost sphere. So essentially, the idea is, as the outer spheres are the ones whose geometry deform the inner spheres, the data should be most concentrated on those, so we get the least deformation, we minimize the distortion, and we stay close to the polysphere geometry, the original polysphere geometry. And I might add, I mean, for a linear model space, it's clear we can just use the exponential map. We don't have such a concept for a spherical model space, and this is the reason why we do this somewhat involved construction. Okay, so just to do this explicitly, we multiply the north pole of the outer sphere with the coordinates of the inner sphere. And for different radii, we rescale the coordinates with the radii, but we do not rescale the north pole of the north pole direction of the outer spheres with the radius, because otherwise we would also scale the inner spheres with the radii of the outer spheres, and we don't want that. And this yields an ellipsoid, essentially. And to get from this ellipsoid to a sphere, we just normalize all the vectors, and this may not be the best way. And yes, well, we're currently working on improving that. But okay, but we get finally a sphere with the geometric mean of the radii as a final step. So as an illustration, we start from such a torus, a donut, then we approximate this by this, we map from the blue polysphere to the green ellipsoid, and then to the red sphere here. And this point here is supposed to be the joint north pole of the polysphere, so the kind of the center point of our construction, or the point where we attach our tangent sphere, if you will. And for dimension reduction, we use principal nested spheres, which have made a very brief appearance before, so I'll just give an overview of what this means. We determine a sequence of subspheres, but not only great subspheres, so not only totally geodesic subspaces, but essentially also small subspheres. And this is what I meant in the sense that spheres are kind of nicer for dimension reduction than linear spaces, because you have an additional degree of freedom by changing the radius of the subsphere, and you still stay in a space of the same structure, which is not possible for linear spaces in this sense. And the recursive construction is done by fitting using the sum of squared geodesic distances. It's very simple kind of Newtonian minimization procedure. At every projection step, we save the signed projection distance, so the so-called residuals, kind of as the information of what we do to our points during our dimension reduction. And the parameter space of this dimension reduction step has dimension d+1 compared to linear PCA where the dimension is only d. And this is, as I said, due to the possibility of taking small spheres. And okay, now let's come to our application and to see whether this gives us any benefit. So what I speak here about is the skeletal representations. These are shape representations consisting of a two-dimensional mesh of skeletal points and spokes going from these skeletal points to the surface, one up, one down, and if you're on a boundary point, you also go one spoke to the boundary, so to the equator, if you will. And so this consists of points and orientations. And these the parameters of such an SREP are the size of the centered mesh, the spoke lengths, the normalized mesh points, and the spoke directions. So this here is kind of the shape sphere. So we use registered shapes here. We don't work with Kendall's shape space, but with a simple registered shape space, which is just a high-dimensional sphere. And these are the directions of the spokes. And so we also only focus on this part here of the data and deform this here to our high-dimensional sphere. And then we compare this to a method that is currently used by the SREP people for dimension reduction, namely CPNS, where they do PNS on each of the spheres of the polysphere individually, and then do a linear PCA on the joint residuals. So this is where the residuals, the distances to the spheres come in. And so the bulk of the dimension reduction, and so essentially the correlation among the different spheres is only done by linear PCA, whereas in our case we first deform our polysphere to a sphere and then apply PNS on the whole thing. And what we achieve is we need much less components to get down to a certain rest of unexplained residual variance. So we need less than half of the components here for a test data set of hippocampi SREPs. And so to explain how this comes about, let's look at a simpler model where we don't look at real data, but at at simulated data, so that it's lower dimensional and one can more clearly see what happens here. So we're looking at a simulated twisted ellipsoid, and we look at the scatter plots of the three leading components. So on the right-hand side, let's start with CPNS. On the right-hand side with CPNS, we see we get this V shape in the first two components, and we also have some variance left in the third component. And this V shape has well, it obviously really spreads over two dimensions. But if you look at it, you would say it's still a one-dimensional thing, and linear PCA cannot capture this, of course. And so we come a little closer to that. We have really more than 90% of the variance captured with a first component, so less than 10% residual variance, and the V shape turns into a 3. And to see why this happens, we can look at the two-dimensional projection we have for our deformed approach, which unfortunately doesn't display very well on the Adobe Reader. I'm sorry. So here are the data points, which are unfortunately hard to see now. And the blue circle is the best fit circle for PNS. So what we see is we still have the V shape in the two-dimensional representation, Only now we're not in a linear setting, but we're on a sphere because we did this whole deformation thing. So we have we brought our correlation between the individual spheres into this spherical setting. And therefore we can approach this V by this circle, and this the overshoots about the circle just produce this 3 shape. And so this is just the point of all of this is that we have a higher dimensional parameter space, namely for a full set of PNS dimension reductions as compared to linear PCA, we have dimension of d-1 higher, and therefore we can approximate the data more closely. Yes. So in conclusion, we propose deformation procedure, and we aim at minimizing geometric distortions, and by this we achieve better and low dimensional representations than CPNS, and this is rooted in the higher parameter space dimension. So that's all. Thanks.
Thank you. So I think we have time for 1 or 2 questions. So. Yeah?
So can you go back to the slide where you have the torus and you fitted an ellipsoid and a sphere?
Do you mean this or the one?
This. Okay. So I'm not sure if I interpret it correctly, but so if you have data on the torus, then they get projected to the ellipsoid and then the sphere, right? So if you take a data point that is very much to the right now, like
yes.
Why does that end up?
Yes, I'm sorry. So for our SRAP application, the data are essentially confined to half spheres. So that's true. If we have data not confined to half spheres, we get, well, it's feasible. You know, you just get a stratified space, and you have to keep track of that essentially. So each data point gets kind of a binary string in which stratum it lies, and so on. But otherwise, you can essentially do the same thing. But it's true. For the sake of this talk, let's just assume the data are always confined to half spheres. So.
And so if it's okay, so say it's on the left side, and but it's still sort of, I don't know, towards the top. Would it then be at the end of the ellipsoid that it gets?
Yes. So
yeah.
So a point. Let's say we have a point here and a point here. They will both be very close to this tip of the ellipsoid, and this is exactly this kind of very strong distortion, of course, that you get. Where is it? Here, right, at the very boundaries of the sign, for close to 0 or close to pi. And this is exactly what we try to avoid by using this data-driven sorting of the spheres. But this is true. I mean, for general data, if they are very spread out, you will get into trouble. And you will have quite large distortions. But the same is true for tangent space approaches. So this is really something where I would contend we're no worse than for example. Yeah. Yes.
Okay, so I think that we are on time. So maybe we have time for just 1 question during. No? Okay. So thank you very much.